Hello everyone, welcome to this part of tutorial about differentiation. In the previous part we learned about general differentiation and differentiation of a constant, differentiation of ax where a is a constant, differentiation of x to the power n and ax to the power n. Also we discussed about whether the differentiation is distributive across addition and subtraction. So in this part of tutorial we are going to learn about stationary values, turning points, and investigating the nature of stationary values. A stationary value of a function f of x is any value of f of x at which its rate of change with respect to x is 0. That is, the stationary values of f of x occur when differentiation of f of x with respect to x is 0. For a graphical representation of a stationary value, consider this curve whose equation is y equals to f of x. At a stationary value of f of x, dy by dx equals to 0, which is the differentiation of y with respect to x equals to 0. So that is the gradient of the curve is 0. And also the tangent to the curve is parallel to the x-axis. Therefore, stationary values of f of x are the values of the y-coordinates of points on the curve y equals f of x, at which the tangent is parallel to the x-axis. So if you consider this example, find the stationary values of x cubed, take away 3x squared plus 2. So if f of x is equivalent to x cubed, take away 3x squared plus 2, then differentiation of f of x with respect to x is equivalent to 3x squared, take away 6x. So at the stationary values of f of x, the differentiation of this f of x with respect to x equals to 0. So if we equate 3x squared take away 6x to 0, then by taking the x out and factorizing would give us x times bracket x take away 2 equals to 0. So that is the stationary values of x cubed take away 3x squared plus 2 occur when x equals 0 and when x equals 2. So these stationary values are f of 0 equals to 2 and f of 2 equals to 2 cubed take away 3 times 2 to the power 2 plus 2, which equals to negative 2. So the stationary values occur at 2 points on this curve, which are 0, 2 and 2, negative 2. So as the stationary values are got at these points, the gradient of y equals f of x is 0 at the point 0, 2 and 2, negative 2. Turning points. The gradient of a curve can be 0 at several points. The shape of the curve in the immediate neighborhood of one of these points belongs to one of the three categories which we are going to discuss now. Moving along the curve in the positive direction of x-axis. In the neighborhood of A, the gradient changes from positive through 0 at A to negative. So A is called the maximum turning point. The y-coordinate of A is called the maximum value of y or the maximum value of f of x, where y equals to f of x. In the neighborhood of B, the gradient changes from negative through 0 at B to positive. So B is called the minimum turning point. The y-coordinate of B is called a minimum value of y or the minimum value of f of x. Also note that the gradient at the maximum or minimum turning points must be 0. Also that the terms maximum and minimum values are not synonymous with greatest and least values. Maxima and minima apply to the behavior of a function in the immediate neighborhood only of its stationary values. The curve does not turn at C. That is, although the gradient is 0 at C, it does not change sign when moving through C. However, the sense in which the curve is turning does change, from clockwise to anti-clockwise. Any point on a curve at which the sense of turning changes is called a point of inflection. And apart from C, there are two other points of inflection, one between A and B, another between B and C. Thus, the gradient at a point of inflection is not necessarily 0. Investigating the nature of stationary values. So if we consider the 3 points on the graph y equals to f of x, so A has a maximum value, and if we take 2 points on either sides of the point A, which are a1 and a2, the value of y at a1 is less than the value of y at a. And similarly, the value of y at a2 is less than the value of y at a. So both the values of y at a1 and a2 are less than the value of y at a for this maximum point A. So if we consider the minimum value, which is b, And similarly, if we take 2 points on either sides of the point B, which are B1 and B2, the value of y at B1 and the value of y at B2 are both greater than the value of y at B. And now if we consider the point of inflection, which is the point C, and if we take 2 points on either sides of the point C, C1 and C2, the value of y at C1 is less than the value of y at C, but the value of y at C2 is greater than the value of y at C. So here, one point has a lesser value and the other point has a greater value. Now, if we summarize the nature of the stationary values, both the values of y on either side of stationary value for the maximum point are smaller. Both the values of y either side of stationary value of a minimum point are larger. But for the inflection, one value is smaller and the other is the larger. Now let's consider the behavior of the gradient dy by dx. For a, at a1, dy by dx is positive, and at a, dy by dx is 0. At a2, dy by dx is negative. For b, at b1, dy by dx is negative. At b, dy by dx is 0, and at b2, dy by dx is positive. For c, at c1, dy by dx is positive. At c, dy by dx is 0, and at c2, dy by dx is positive. That is, for a maximum point, the sign of dy by dx moving through the stationary value is positive at the beginning and then 0, and negative at last. For a minimum point, it's negative at the beginning and then 0, and the dy by dx is positive at the end. For inflection, there are two types. One is where both the dy by dx values are positive on either sides of the stationary value, and the other is both the dy by dx values are negative on either sides of the stationary value. So at first we considered the values of y to investigate the nature of the stationary values, and now we have considered the behavior of the gradient dy by dx, and next we are going to consider the second derivative of y with respect to x. So when passing through a, dy by dx changes from positive to negative. That is, dy by dx decreases as x increases, or the rate of increase with respect to x of dy by dx is negative. So that is, derivative of dy by dx with respect to x is negative. So this clumsy notation for the rate of increase with respect to x of dy by dx is condensed to d2y by dx2, which is known as the second derivative of y with respect to x. Similarly, when passing through b, dy by dx changes from negative to positive. That is, dy by dx increases, or d2y by dx2 is positive. So points of inflection are not so easily dealt with this third method. It is true to say that d2y by dx2 is 0 at such points, but d2y by dx2 can also be 0 at maxima and minima points. A more detailed analysis of points of inflection will be carried out later. So according to the third analysis, the sign of d2y by dx2 at the maximum point is negative, or 0. But at the minimum point, the sign of d2y by dx2 is positive, or 0. So all these three methods of analyzing the nature of the stationary values are very important, and out of them the first two are the most accepted methods, as the third method fails if at a stationary value of y, d2y by dx2 is found to be 0. So in this case, either of the first two methods has to be used. Now pause the video and try out this question by yourself. Okay, find the points on y equals x to the power 4 plus 4x cubed take away 6 at which the gradient is 0, and determine the nature of these points. So we are given with the equation of the graph, which is y equals x to the power 4 plus 4x cubed take away 6, and also we are asked to find the points where the gradient becomes 0, and in addition to that we have to determine the nature of the points. So if y equals to x to the power 4 plus 4x cubed take away 6, and we take it as the first equation, then dy by dx, which is the first derivative of y with respect to x, equals to 4x cubed plus 12x square, which we take as the second equation. And also the second derivative of y with respect to x equals to 12x square plus 24x. So we have learned how to differentiate the expressions with respect to x, so that we have got all these equations, and also we have got the third equation. So the gradient of the curve equals to 0 when dy by dx equals to 0. So that is when 4x cubed plus 12x square equals to 0. Now finding the roots of this equation, we get x equals to -3 and x equals to 0. So the gradient becomes 0 at 2 points where x equals to -3 and x equals to 0. So when x equals to -3, dy by dx equals to 0. And from the third equation, by substituting -3 for x, we get 12 times -3 to the power 2 plus 24 times -3 equals to 36. So we have got a value which is greater than 0. So when we get a value which is greater than 0 for d2y by dx2, by the knowledge that we have got from the explanations that this point has a minimum value, and from the equation 1, by substituting -3 for x, we get the y value of the particular point, so which equals to -33. Therefore the points with coordinates -3, -33 is a minimum turning point. Moving on to the next point where x equals to 0, dy by dx equals to 0, and the y value of that point equals to -6. Since the value of d2y by dx2 equals to 0 for this point, we are not able to find it out whether it is a maximum, minimum, or inflection point. So in addition, let us now see what the sign of dy by dx is on either side of the point where x equals to 0. So by taking a value less than 0, which is -1, and substituting that in the dy by dx, we get a positive answer. So by substituting -1 in the equation dy by dx equals to 4x cubed plus 12x square, we get 4 times -1 cubed plus 12 times -1 square, which equals to 4 times -1 plus 12 times 1, which is 12. So -4 plus 12 equals to 8, which is a positive value. So the slope is positive. And at the stationary point, dy by dx equals to 0, and the slope looks like this, which is parallel to the x-axis. And when a value which is greater than 0 is substituted for x in the equation dy by dx equals to 4x cubed plus 12x square, we get 4 times 1 cube plus 12 times 1 square, which equals to 4 plus 12, which is 16. So again we are getting a positive value. So the slope looks similar to the one which we got for -1. By combining these slopes at the point and marking the point 0, -6, we get an inflection point. So 0, -6 is a point of inflection. Now pause the video and try out this question by yourself. Sketch the curve y equals to 2x cubed plus x square, take away 4x plus 1. So finding the maximum and minimum turning points will help to give a general idea of the shape and the position of this curve. So if we take y equals to 2x cubed plus x square, take away 4x plus 1, then the first derivative of y with respect to x equals to 6x square plus 2x, take away 4. And the second derivative of y with respect to x equals to 12x plus 2. So we have already learned how to differentiate a function with respect to x. Now at the turning points, dy by dx equals to 0. So that is 6x square plus 2x, take away 4 equals to 0. By factorizing this equation, we get 3x take away 2 times x plus 1 equals to 0. And by finding the roots, we get x equals to 2/3 and x equals to -1. which means we have two stationary values. When x equals to 2/3, dy by dx equals to 0. And by substituting x equals to 2/3 in the equation d2y by dx2 equals to 12x plus 2, we get d2y by dx2 equals to 12 times 2/3 plus 2, where we get an answer which is greater than 0. So if we get a positive value for d2y by dx2, it means this point is a minimum turning point. Now by substituting x equals to 2/3 in the equation y equals to 2x cubed plus x squared take away 4x plus 1, we get the y equivalent value of this point, which is y equals to negative 17 over 27. Therefore the point 2/3 comma negative 17 over 27 is a minimum turning point. So let's consider it as the first information. Now moving on to the next point, where the x value is negative 1, we get dy by dx equals to 0. Then by substituting x equals to negative 1, find out d2y by dx2, we get d2y by dx2 equals to 12 times negative 1 plus 2. So by simplifying, we get a value which is less than 0, which takes us to the conclusion that this point is a maximum turning point. And by substituting negative 1, find out the value of y, we get y equals to 4. Therefore the point negative 1 comma 4 is a maximum turning point, and we take it as the second information. As y equals to 2x cubed plus x squared take away 4x plus 1, the curve cuts the y-axis at 0, 1. So this is because to find out the point at which the curve cuts the y-axis, we substitute x equals to 0 in the equation of y. So we get y equals to 1. Or we can simply find out the intercept of the curve by finding out the value which does not have any x terms, which is plus 1. So that shows the intercept at which the curve cuts the y-axis. So we take it as the third information, and by combining all these three information, we sketch the curve as the one shown here. So we have the point at which the curve cuts the y-axis, and we have the maximum point where x equals to negative 1 and y equals to 4. Then we have the minimum point where x equals to 2/3, then y equals to negative 17 over 27. So this is how we analyze dy by dx and d2y by dx2 of the equation for the curve to sketch the curve. So that's it for this tutorial. I hope you enjoyed learning about stationary values, turning points, and investigating the nature of stationary values. If you liked the video, press the like button. If you have any comments, please put them in the comments below. And also subscribe to Easy Maths tutorials to get instant access to the videos. I'll see you in the next tutorial. Thank you.